In this lesson, we'll learn about fluid materials. We'll learn about their density, their upthrust, viscosity, laminar and turbulent flow, terminal velocity, Stokes law, and viscous drag in this video. So starting from the basic, we have to define what a fluid is before we learn about it. A fluid is anything that can flow. Air is a fluid because when there's wind, air is flowing. Water is also a fluid. When we pour water, it flows in rivers, in seas, or if you pour water on the table, it will flow down. Honey is also a fluid. Slime is a fluid. So basically, fluid is anything that can flow. Sand can also behave as a fluid. So you know about the hourglass. So the sand clocks. If you flip the hourglass, the sand will start falling through here. So if I turn it upside down, the sand will be up here and it will fall down and it will be acting like a fluid. So even if the particles themselves are solid, they might exhibit fluid behavior. So usually fluids are any gases or liquids, but in certain cases like this, fluids can also, like tiny solid particles, can also start behaving like fluids. So this is how we describe a fluid. Any substance that can flow. The density of this fluid would basically be the mass per unit volume. So density is written as the Greek letter rho. This is mass by volume. Now coming on to the most important feature of a fluid that we'll study, this is upthrust. Upthrust is the reason that things can float. So anything that floats is due to upthrust. So when ice is floating over here, this is due to upthrust. If there was no upthrust, there will be a downwards weight of the ice, so it would sink. It would accelerate downwards and sink. It doesn't sink because the fluid gives it an upward force, which we call upthrust. We write down upthrust as U. When anything is submerged in water or any fluid, it feels an upthrust. So even in air, anything in air will feel an upthrust from air. Air is less dense than water, so the upthrust is less in air than water. And this upthrust will be the mass of fluid that is displaced. So for this ice cube, this is the amount of water that it moved away. So before the ice was here, this place was filled with water. But now since the ice is here, it removes the water from here. So it removes the water that was in this blue region. That is the water displaced. So this is the water displaced. We can find its volume V. Using that, we can find the mass or weight of water that was displaced. Since upthrust is a force, it would be the weight of water displaced. From here we know that the mass of water displaced will be the volume times the density of water. We know that density is mass divided by volume. So mass will be density multiplied by volume. So we apply it over here. The mass m of water displaced will be equal to the volume of water displaced times the density of water. Not ice. We want the density of water since we want to find the weight of water displaced. So mass of water is density of water times V. So upthrust is the weight of water. If I multiply both sides with G, I get mass of water times G. This is the weight of water displaced or the upthrust. This was when water is the fluid. So for any fluid, Upthrust will be the density of the fluid multiplied the volume displaced times g. This is also the reason why ice cannot float like this. So when ice floats, some of it is under the water. So when ice floats, it's something like this. The ice is partially under the water. This part is under the water. Anything doesn't float like this, because here the volume of water displaced is 0, so there is no upthrust. So 0 upthrust. So there is a downward force due to the weight. So weight upthrust is 0. So after some of the ice has sinked, the upthrust becomes equal to the weight. So we have weight minus upthrust equal to 0. So resultant force is 0 over here. So the ice doesn't move any further. Now we'll learn about the two different types of flow. So we have two different types of flow. One is laminar, the other is turbulent. Laminar flow is a smooth flow. This happens when an object is moving slow. Laminar flow is predictable. Turbulent flow is the opposite. Turbulent flow is the flow of air during storms, for example. The air will move erratically. So if it's in other forms, so if it's in water, the liquid will move erratically. So basically, in turbulent flow, the fluid moves erratically, while in laminar flow, it has a smooth flow. Laminar flow happens when you open your faucet lightly. So if you go in front of your sink and open the faucet gently, the water will fall like this. If it's slow enough, it will look like the water is not falling at all. So that is laminar flow. In laminar flow, the velocity at each place is a constant. So if this is a pipe and water is going through it, on the edges the water will move slowly than in the center, because it will face some friction with the walls. However, at the same place the velocity will remain constant however time goes. So even 5 seconds later, the velocity at the edges will still be the same. The velocity at the center will still be the same. We also call laminar flow streamlined flow. Streamline is basically having this constant velocities. This is a laminar flow. It generally occurs at low speeds, and the velocity at a point remains constant at all times. So even after an hour, if I keep the flow like this, the velocity at this point will remain the same. The velocity at this point is different from the other point. So the velocity at the red point is different from the white point. But after 1 hour, if I keep the flow same, the velocity at the white point will remain the same as it was an hour ago, and the velocity at the red place will also remain the same as it was an hour ago. So even if the velocities are different between these 2 points, they are the same throughout time at each of them. These lines of velocities are called streamlines. That's why laminar flow is also called streamlined flow. Now if I go to turbulent flow, turbulent flow is the opposite of laminar flow. It happens when the speed is very high. The fluids behave erratically. So if you think about a storm or a tsunami or waves hitting the shore, they behave pretty randomly. They don't have a general speed and they keep changing. So if I draw turbulent flow in a pipe, it will be something like this. So a random chaotic stuff hitting each other. So something like this, and the velocity at a point will not be constant, it will continuously keep changing. If you stand outside when there's a storm going on, you won't feel the same velocity of wind all the time. Sometimes the wind will be very strong. A few seconds later the wind will be slow, and then the wind speed will again rise. So in turbulent flow this happens. So there isn't a constant speed at a point, it continuously changes. So they generally occur at higher speeds, and the velocity at a given point changes over time. This is a turbulent flow. Now we have to learn about streamlining. Now if an object shows a laminar or turbulent flow depends on several factors. One depends on the viscosity and density of a fluid, and it depends on the shape the fluid is traveling or flowing through. So for example, if I have a car that's shaped like a box, when it goes to the right, it hits the air particles, so the air particles move like this. When the air particles hit the car, if it's a box shape like this, it will the wind will instantaneously have to make a new turn. So it will hit the car and then return. This will cause there to be a conflict. So some of the air is coming from the left while the other air is bouncing back to the right. So they will collide and there will be turbulence over here. So the flow will become turbulent over here. This is why cars have a shape like this. So in general cars are shaped like this. So now if the wind comes, it just follows the car's shape and goes like this. This is how the air particles move if the car is streamlined. So this shape is called streamlining. So the wind coming or the air coming just goes over the car and back. So in this case it can maintain a laminar flow. In laminar flow gives less resistance than turbulent flow. If there is turbulent flow, there is more resistance to the car's motion, so more fuel needs to be used to overcome that. If the car is streamlined, it faces less resistance, less air resistance, so it can save more fuel and reach higher speeds. That's why Formula 1 cars or race cars are generally shaped very thin at the front and then gradually goes up. Up next we'll learn about viscosity. Viscosity is basically how easily a fluid flows or how hard it is for a fluid to flow. So the greater the viscosity, the harder it is for the fluid to move. So for honey, for example, if you try to pour honey from a jar, it will take much longer than it will for water. So honey has a higher viscosity than water. Viscosity is basically resistance to flow. So this is what viscosity is. The resistance of a fluid to flowing. Now there's a value, we attach a value to it, so we call it the coefficient of viscosity. This is just a numerical value for the resistance of the fluid, and we write that with the Greek letter eta. So coefficient of viscosity, it's basically a numerical value given to quantify a fluid's viscosity, and it's written by the Greek letter eta. Now we need to learn about practical to determine viscosity. So to set up the experiment, we'll have a water container. We'll have to have a water supply to it from down here. Now I want to maintain a constant water level on it, so I'll put a pipe through it at this level. If I put a pipe at this level, if the water rises, it will just get sucked in by this pipe and it will be drained out, so the water level will remain constant. And then we'll have a capillary tube through here, and our output. We'll take this in a measuring cylinder so we can measure the volume. So some of the water will come out through here and then fall here. For this experiment, we need this height of the water up to the capillary tube. We need the length of the capillary tube, so from here to here, this length L, and we need the density of water. Now we have to plot a graph of the flow rate. So from here we measure the volume. So if I take the volume filled in the measuring cylinder for 10 seconds, so from there we get the flow rate. The flow rate is volume per unit time, so how much water is leaving per second or per minute. Now we'll keep on changing the height by adjusting this pipe over here and plot a graph of the flow rate against H. And we have to remember that the gradient of this graph will be pi times the density of whatever liquid we are using or fluid we are using times G times the radius. Okay, we need the radius of the capillary tube as well. So from here the radius, so the radius of the capillary tube is R. This is to the power 4 divided by 8 times the viscosity times the value of L. From here we can make eta the subject. We'll have pi rho g r to the power 4 divided by 8L into gradient. From here we can find the viscosity of a liquid. This equation over here is called Poisson's equation. The spelling is, this is Poisson's equation. This is a core practical we need to learn. Now moving on, we have to learn about Stokes' law and terminal velocity. Stokes' law works when there is a spherical object or a small object. If it's a small object, it doesn't necessarily have to be a sphere. So a spherical object moving through a fluid in laminar flow. The Stokes' law, using Stokes' law, we can find the drag force when the conditions are met. Then the drag force or the viscous drag. Viscous drag is basically the drag due to the fluid. This is equal to 6 pi eta RV. Eta is the viscosity of the fluid. R is the radius of the sphere. And V is the terminal velocity. If we want terminal velocity, this is just the velocity when we are considering it. Now we have to learn about terminal velocity. Terminal velocity is the velocity at the constant velocity at which an object falls. So if an object starts falling through a fluid, we have the weight acting downwards and the upthrust acting upwards. So for example, a skydiver, this is a skydiver, his weight is acting downwards, his upthrust is smaller than his weight and acting upwards. Since he is moving downwards, the viscous drag or air resistance or viscous drag due to the fluid will be upwards. So this force over here, we can write it as D or F, either one. As the velocity increases, if we look at this equation, as the velocity increases, the viscous drag will increase. So if I increase the velocity, the viscous drag increases. The viscous drag keeps increasing and increasing until the upward force and downward force become equal. Before, we had a resultant downward force without the viscous drag. When it wasn't here, we had a resultant downward force. So the skydiver is accelerating downwards. However, when his upthrust and viscous drag become equal to the weight, his resultant force becomes 0. If the resultant force is 0, his acceleration becomes 0, so he reaches a constant velocity. This constant velocity is called the terminal velocity. Terminal velocity is specifically used only when an object is falling due to gravity. So terminal velocity is the velocity of a falling object when its weight is balanced by viscous drag and upthrust. So the point at which its resultant force is 0. Now for spherical objects falling, so for example, we have a core practical where we drop marble balls through a measuring cylinder which is filled with glycerin. Glycerin is a high viscosity liquid, so we can reach the terminal velocity really fast. If it was air, we need a few kilometers to reach the terminal velocity. So after a while, so for example, when the ball is over here, it reaches its terminal velocity. Using a light gate at the end, we can measure this. So we put a light gate over here at the end and measure the terminal velocity. Usually, since this is a sphere, we use 2 light gates. So we can measure the velocity between these 2 heights. If I want to check if it has reached terminal velocity, I'll just move the light gates a bit up or down. So I can move the light gates up or down. If it has reached terminal velocity, it has a constant velocity. So even at this point, it will have the same velocity as this point, and the same over here. So we'll find the same velocity at 2 pairs of points. So I can take this red 2 pairs and then measure the velocity between the blue points. I'll find the velocity between these 2 blue points and these 2 red points. If they're the same, I can be sure that it has reached terminal velocity. We can measure this velocity. Now when terminal velocity is reached, we know that the weight is equal to the upthrust plus viscous drag, so F or D. The weight is mg. If I don't know the mass of the ball, I can just use rho solid times the volume times g. I need to figure out the volume of the fluid, the volume of the marble balls or the steel balls. The steel balls are usually used. So I have to find the diameter. Using the diameter, I'll find the volume. So the volume is basically 4 by 3 pi r cube. R is d by 2. So 4 by 3 pi times d by 2 cube. This is the volume. The upthrust will be the density of glycerin over here, or any fluid we use. So we have density of fluid times the volume of the steel ball times g plus the viscous drag. This will be 6 pi eta rv. This is another method of finding the viscosity. From here, I can take 6 pi eta rv on one side, and we have v times g, density of solid minus density of fluid on the other side. So we are sending this term to the left, and we have then Vg is common in both of them, and we have density of fluid and density of solid. We'll have this term over here. We can take Vg common from here, write down density of solid minus density of fluid. Now depending on the variable I have to find, I might be asked to find the terminal velocity by having a known value of viscosity, or might have to find the viscosity. If I have to find the viscosity, I'll divide both sides with 6 pi rv. So eta will be equal to v times g, density of solid minus density of fluid, divided by 6 pi rv. If I want to find a v instead, I'll have v equals to vg rho s minus rho f 6 pi r eta. Here the velocity will be the terminal velocity, since we are using this equation over here, which is for terminal velocity. And that's all for this video.